Hello everyone, a very good afternoon. Myself Kumari, Industry Relationship Coordinator at Takshila VLSI Technologies. Welcome to today's VLSI webinar. Before we start, I would like to give a brief introduction about our institute. We Takshila Institute is a leading VLSI training center in Bangalore and Hyderabad. We offer special courses helps you learn important skills in the VLSI field. We offer physical design, analog layout design, analog circuit design, ASIC verification and design for test. Why to choose Takshila? Here are some of our unique features. We provide 24/7 tool access and VPN support for continuous practice. Hard copy materials are provided to enhance your learning experience. Experienced trainers. Our trainers have over 10 plus years of industry experience. Placement support. We offer 100% placement assistance until you secure a job in the VLSA or semiconductor industry. Our candidates have successfully secured positions with leading companies such as Micron, Synopsys, Intel, Insemi, Onsemi, Wipro, etc. Today's webinar will be presented by Sunita ma'am. Ma'am have over 5 plus years of industry experience and currently works as a physical design engineer. Now I'll hand over this session to Sunita ma'am to continue the webinar. Thank you.
Hello everyone, very good afternoon. I am Sunita, currently working as a physical design engineer in well-known company with overall 5 years of experience in VLSA industry. I have worked on various stages in physical design flow like floor plan, power plan, placement, clock tree synthesis, routing and many timing closures using industry standard tools such as design compilers and IC compilers. Also, I am a mentor at Takshila Institute where I support the students to understand the basics and guide them towards a career in semiconductor field. In today's section, I am taking you through webinar on job opportunities in VLSI or semiconductor industry. So let's get started. So agenda. So here we are discussing about VLSI or semiconductor industry introduction and eligibility criteria for VLSI jobs. About Takshila VLSI courses offered and unique features. And core job opportunities, industry salary scope, placement at Takshila VLSI, and later we will entering into some technical part, so which is related to VLSI, AMS and custom IC layout design flow, ASIC or chip design flow, RTL design and verification concepts, physical design flow. The last one is a question and answers. You can ask any questions. We'll discuss. So these are the topics we will cover in this today in this webinar. So terminology. So here we are seeing few words, right? So these words are using in entire VLSI industry. Semiconductors. So what is mean by semiconductors? You know that, right? Semiconductors are lies in between conductors and insulator. So they can act both. So these semiconductors are made up of silicon material. So by adding impurities to the semiconductors, we can use them in VLSI industry. So they are prepared by using NMOS, PMOS structures in the fabrication process. So VLSI. VLSI means very large scale integration. So why we have to know about VLSI? Why we have to learn about VLSI? So before these generations, we came across from several generations like small scale integration, medium scale integration, and large scale integration. So in small scale integration, we used only hundreds of transistors for making an IC. So now, as the technology increasing, we are decreasing the size of a transistors and increasing the count of transistors in a particular area. So we came for medium scale integration, that is we used only thousands of transistors for making an IC. So here, after that, we came for large scale integration. Here we are using millions of transistors for making of a single die. So what is meant by technology and why we are increasing the count? We'll discuss here. And chip or IC means integrated circuit. ASIC, application specific integrated circuit. So we are using integration, right? So what is mean by integration? So we are placing millions of transistors at a particular area. So that is known as an integration. So now we are using the billions of transistors for making a single die. So ASIC, why we are calling ASIC? So ASIC is a application specific integrated circuit. Different devices, we are using different ICs. We are not using only one IC for all the applications, right? So for mobile, we are using particular IC. For laptops, for gaming laptops also, we are using a particular ICs. So like that, different applications have different ICs. So here we can see it is an IC. So where the chip or ICs are used? So in almost all the electronic equipments nowadays, we are using an ICs. So like for example, mobile, laptops, TV, satellites, cars, almost all electronic equipments today we are using an ICs for calculating smartphones or watches, digital calculators also we are using ICs nowadays. How a chip interiors looks like. So you observe gates, right? So AND gate, OR gate, inverters, some logic gates in your DLD lab or IC lab. So there they are packed with covered with plastic package, right? So that is known as a plastic package, black color part. So it is used for not allow any damage to the internal device. So for the protection purpose, we are using the plastic package. So here we can observe this one, it is a semiconductor die. So where billions of transistors are integrated in the particular area. So that is known as a semiconductor die. And here, these are yellow lines. So we call them as a gold bond wires. So why we are using gold? Means it is a good conductor of electricity as compared with other metals. So that's why we are using gold. And these pins are external pins that are used for the communication between the external device to the internal die. The size of an IC is 5 into 5 mm. So how this like this the interior chips look. Semiconductor wafer. So what is mean by wafer? Why we have to learn about the wafer means? So in the wafer only we are manufacturing all the ICs. So for our particular application, we are using many ICs. So here we can see that, right? These are the boxes. So one box is known as one IC or chip or die. So we are manufacturing at a time many ICs for one applications. So the size of a wafer is 12-inch wafer. It is made up of a silicon material. So it is having P substrate, dopants, etching, silicon, everything is done on this wafer only. So all the semiconductor chip dies are made on this wafer in the fabrication process. How many chips are integrated? So when we are starting manufacturing of an IC, that is in 1970 we started. In that year, we used only 5,000 transistors for making a single die. But today, we are using 100 billions of transistors and MOSFETs are integrated to manufacturing of an IC. So here we can see this is an internal structure of a MOSFET. So it is having P substrate, dopants of N well and P well. We are applying the external voltage and providing the gate, source, everything. So in your recent textbook of VLSI, you may observe that. So VLSI introduction. So before we are going to know about VLSI, we have to get the idea of Moore's law. So what is mean by Moore's law? So Moore's law is the observation that the number of transistors in a dense integrated circuit doubles about every 2 years. So when we are manufacturing something, We used only 10 transistor this year, and after 2 years, that count is double, means it is 20. So that observation is named after the Gordon Moore, the co-founder of Fairchild Semiconductors. So by their observations, they prepared one graph. So here we can observe that in 1917, the Intel company starting manufacturing of an IC with the help of 5,000 transistors. The same company, after 2 years, it increased the count, but the area is same. So here we can observe. So in 1972, it increased the count of a transistor, that is 10,000. So like that, every company, not only Intel, Motorola, some ARM companies are starting manufacturing of an ICs. 1 year this much count, and after 2 years they increase the count. But today we are using billions of transistors for making an IC. Integration made is possible. So what is mean by technology? So we'll discuss in later slides. So technology is enabling us to reduce the size of each transistor and MOSFET. So here we derive the technology from the MOSFET scaling or process nodes. So in 1971, the size of a transistor is 10 micron meter. So it is little bit big. After that, after 2 to 3 years, the count is decreased. I mean, we are increasing the transistor count and the technology size is decreased. That is 6 micron meter. So like that, in 1987, it is 800 nanometer. So the technology is decreased, right, from 10 micrometers to nanometer, 800 nanometer. So like that, every 2 to 3 years, the technology is decreasing and we are increasing the count of transistors. So let us observe some of them. In 2001, it is 130 nanometer, 2007, 45 nanometer, 2012, 22, 2018, 7, 2022, 3, and 2024, 2. Now we can use 1 nanometer or 0.8 nanometer also, or 5. So in future, we can use this technodes also. So what is mean by 1 micrometer? 1 micrometer is 1 millionth of meter and 1 nanometer is 1 billionth of meter. So these are the readings while considering the design. What is technology node or tech node? So the size of a transistor in a chip is known as a technology size. How we are defining the size? So here, it is the structure of MOSFET. So when we are applying the external voltage to the drain, there is a formation of channel, right, from drain to source. So the distance between source to drain is known as a technology node or tech node. So that may be 32 nanometer, 28 nanometer, and 65 nanometer. It may be any size. So typical tech nodes used in the productions are 28, 32, 45, 65, and 90. So about 28 nanometer technologies, we are using the MOSFET technology. So any size lower than 20 is FinFET techno, which is lower than 28, means that may be 3, 5, 7, and 14. So lower than 28 nanometer technologies, we are using the FinFET. Why? Because we are having many advantages for the FinFET as compared to the MOSFET. Like they will consume less power, they will provide less delay, and it is a multi-directional power as compared for the MOSFET technology. So that's why we came for FinFET technology for lower tech nodes. Semiconductor industry demand drivers. So here, there is a demand for the semiconductor industry by these end markets. So for computing, we are having demand for semiconductor industry, that is 34%, and for wireless communication also having 30% of demand, and consumers like mobiles, laptop, TVs, all the applications are having some demand of 14%, and autos, industrials, wired communications, and military and aerospace. So all these are having the demand for the semiconductor industry. So VLSI or semiconductor industry growth. So we can observe here every year we are having a 8.6% of growth in the semiconductor industry. So we can see the graph here. So semiconductor market size 2023 to 2033. So let us observe in 2023, the growth of the semiconductor industry is $544.78 billion. After 1 year, means in 2024, it is increased a little bit, right? $584.17 billion of growth. So after 10 years, that is in 2033, it may be increased to $1,137.57 billion of growth. So every year there is a growth and demand for the semiconductor industry nowadays. VLSI or semiconductor companies. So as usual, we know the software companies, right? Along with that, some of the companies are present in the VLSI also. So they are categorized into three types. What are they? Means product-based companies, EDA companies, and service-based companies. What is the work of the product-based companies? Means they will do the projects and fabrication of an IC. EDA companies means these companies will provide the software or tool for making or designing of an IC. So they will provide the tools. And service-based companies. So the name itself it is saying that it will give you the service to both EDA companies and product-based companies. So what happens when we don't have any one of these companies means? So if we don't have project-based companies means who will give the project of designing of an ICs, right? So that is an important and EDA. Without having tools, where we can design the tools. And if there is no service-based companies, means who will give the service? So that's why all these are important in the VLSI industry. So EDA product and service-based companies will always be in a sync up to make the technology deliverables. So with the support of VLSI engineers. Semiconductor industry ecosystem. So based on the functionality, all the companies are divided according to that. So in designing and manufacturing, so in designing, fabless chip forms. So here, the fabless chip forms means they will do the projects, but they can't do any fabrication of physical IC. That companies are known as a fabless chip forms. Example, AMD, Qualcomm, NVIDIA, Marvell, Broadcom. So comes to fabless non-chip forms here. You may get some question, right? It looks like these are the software companies. So where is the use of the VLSI industry? So they are the computing of the VLSI industry. For example, Apple, Microsoft, IBM, Amazon, and Google, Apple. And IP and design software. Here, these companies will provide the tools or software for making of an IC. Synapses, Siemens, ANSYS, ARM, Cadence. So after designing, we have to fabricate them, right? So these are some manufacturing companies like Foundries, Global Foundries, TSMC, Samsung, SMIC, UMs. So to do all this, we need some equipments. So that equipments are provided by ASML, Tokyo Electronics, Applied Materials, and Lam Research. After that, there are some integrated device manufacturers are there. So they are Texas Instruments, Analog Devices, Macron, Infineon, Intel, Samsung. So after all this, we have to check them, we have to test them, we have to assemble and we have to pack them, right? ICs. So to do that particular work also, there are some companies like TR, Amco Technology, Elegant, Lattice Semiconductor and Foxconn. So these are the functionality of each and every company. So top semiconductor product-based companies. So here we can see some of the top semiconductor product-based companies. One is an Intel, NVIDIA, Samsung, Qualcomm, Broadcom, AMD, Infineon, Texas Instruments, MediaTek, and Sony. So here they are having good revenue in 2023 on semiconductor industry. So today NVIDIA is in the top place as compared to the other companies. EDA or CAD companies. So these companies will provide the tool or EDA tool is a software which is used while the designing of an IC or chip. So EDA means electronic design automation and CAD, computer aided design. So why we are using CAD here means, so while designing of an IC, we have to check them each and every part, right? So is there any missing of connections or any errors? So to check them in 2D or 3D format, CAD is required. So these three companies will provide the tools like Karen, Synapsys, Mentec Graphics. Different tools are required for designing of an IC and for testing them for the power and timing. So there are different companies, different tools are there from front end and to back end. So every step in the chip design requires EDA tools. Fab companies. Until now, we discussed about the product based companies. So now we are going to know about the fabrication companies. So one of them is a TSMC, Taiwan Semiconductor Manufacturing Company, and GF, Global Foundries. So every product based company will have their own fab. But some companies are fabless, for example, Qualcomm. Why we are calling Qualcomm as a fabless means they will do the projects, but they can't do any fabrication of physical IC. So that's why we are calling Qualcomm AMD as a fabless companies. So top fabs worldwide. So here we can observe some of the top fabrication companies in the world. So one is the TSMC, which is having the $16.7 billion of growth, UMC, Global Foundries, SMIC, Samsung. So they are all having good revenue on the semiconductor industry in 2023. So 500 plus established VLSI service companies. So here we can observe some of the companies like MNC companies, MNC service-based company, and large service-based company and startup service-based company. In MNCs like Capgemini, L&T, HCL, Tech Mahindra, Wipro, Cyient, these comes under the MNCs. Comes to large service-based company, Mirarpa, Insemi, Mochip, Sankalp, Tensol, Savitech, Perfect VIP, True Chip, Songchronics, all this comes under the large service-based company. So comes to startups like Semiconductor, Savitech, Big Silica, Sign-Off, Swiss Semi, P2F Semiconductor. So all this comes under the startup service-based companies. So what is the use of these companies and why we have to learn about these companies means? So after we are trained, we will get a chance in any one of these service-based companies. After entering into that, they will train us for 3 to 6 months. So after that, they will assign a project in the product-based companies. So we have to go there and we have to work until the project is completed. Again, they will assign a different project in different company. We have to complete that work and we have to come back again to these MNCs companies. So this is a work or this is the way how they are giving the service to the product based or EDA companies. So we are having 500 plus more as companies of service based companies in Bangalore and Hyderabad. So semiconductor IC making video, there is a short video of how the internal process are there for making of an IC. We will see and observe them.
Memory chip design is the first step in the production of Micron's memory chips. This process involves the use of computer-aided design tools to lay out billions of electronic components that store data on the chip according to the product design specification. During technology development, specific process steps are defined and integrated into a process flow that will build the memory chips. The process steps are tested and refined until the process node is qualified and ramped in manufacturing. Individual memory chips, or die, are built upon pure silicon wafers in a fabrication area, or fab. Fabs are state-of-the-art clean rooms that are 100 times cleaner than a hospital operating room to ensure silicon wafers are protected from ambient contamination. Among the many process areas in a fab, the photolithography area coats wafers with a photoresistant material. Then, like film in a camera, circuit patterns are exposed and excess material is rinsed away. The paths in these circuits are 5,000 times narrower than a human hair. Wafers are moved between different tools and processes using a robotic automated material handling system, or AMHS. Each wafer may be moved through more than 1,000 processes. It takes more than 1 month to make a memory chip. In probe, initial functionality tests are performed on each die on the wafer. A probe card positions probe needles onto each die to send and receive test data. This information is used to generate a map of all the die on each wafer. Only good die that pass all tests in probe will continue through the manufacturing process. In assembly, wafers are first thinned, attached to an adhesive backing, and then diced into individual die using a diamond edge saw. Using the wafer map that was created in probe, individual die are picked from the wafer, then placed on a circuit board. A solid gold wire is used to connect each chip to the circuit board. A molding process encapsulates each die in a protective plastic package and shipped to test. Every memory chip Micron manufactures undergoes hundreds of tests to ensure it meets the highest quality standards. Proprietary Ambix testers subject finished parts to extreme temperatures and conditions to force any weak components to fail before they reach our customers. Additional test equipment verifies that each part meets or exceeds its speed and performance specifications. All qualified parts are laser marked with part numbers and other identifying information. Each memory chip is optically scanned to verify strict fit and form specifications. Components are placed into industry standard anti-static packaging and placed into boxes for shipment. Many of Micron's finished parts are used to build memory modules and solid-state drives. Automated surface mount assembly equipment is used to mount memory and other components to printed circuit boards. All products are tested using proprietary Micron memory module and SSD test equipment. Finished products are placed into anti-static packaging before boxing for shipment to the customer.
So eligibility criteria for VLSA job. So BTech and MTech students are eligible for getting VLSA job. So ECE, EEE, ENTC, EA with 60% minimum and should complete any VLSA course. And comes to MTech, VLSA, MLD, electronics with 60% minimum should complete any VLSA course. So about Takshila VLSA Technologies. So here it is the best institute in Bangalore and Hyderabad for freshers and working professionals for advanced VLSA studies with 100% placement assistance till you get placed. So industry standard EDA tools with 24/7 tool support. So tools which are using in the industry, that particular tools are available at Takshila. Faculty and trainers are with minimum 15+ years of experience in the semiconductor domain. So the trainers which are explaining you here, which are giving the training, they are having good experience in the semiconductor field. Collaborated with 200+ hiring companies, 100% placement with training materials and mock interviews. So proven track record of placement with scholarship facilities. So why to select Takshila VLSA? Because we are having some unique features. So what are they means? We are providing 100% placement assistance and 24/7 lab support, low price and scholarship facilities, industry standard course syllabus. So 100% placement assistance, industry standard course curriculum, 24/7 lab support, low cost value for money. So infrastructures and labs in Bangalore. Infrastructures and labs in Hyderabad. So there is a short video of Takshila VLSA corporate video. Watch once. So courses offered often in online for freshers and working professionals. So these 5 courses are available at Takshila. Physical design, ASC verification, analog layout design, design for test, analog circuit design. So training methodology and intake. So for physical design, design for test, and ASIC verification, the duration is 5 months. Daily 2 hours class and lab practice with full-time mentor availability. Number of students are 15 to 30. 24/7 VPN lab access means virtual private network, that is a tool. So it is given by the students. You can practice the design until in 24/7. And LMS portal access. So learning management system, here we are having the recorded videos of your class. If you miss any one of the class means easily you can access and you can read. So 15 plus experience Takshila VLSA full-time trainer and full-time mentor. 100% placement assistance still get placed. So this is about the physical design, DFT and ASIC verification. So comes to analog layout design, the duration is 4 months. Daily 2 hours class and lab practice with full-time mentor availability. Number of students are 15 to 25. 24/7 VPN lab access, LMS portal access. 15 plus experience Takshila VLSA full-time and full-time trainer and mentor available. 100% placement assistance still get placed. So comes to analog circuit design. Duration is 14 weeks. Weekend batch 6 hours per week class and lab practice. Number of students are 10 to 15. 24/7 VPN lab access, LMS portal access. 15 plus experience Takshila VLSA full-time trainer. 100% placement till you get placed. So core job opportunities in PD. So after completion of your course in the physical design, you are become any one of this engineer in this one, like physical design or STA engineer, physical verification engineer, EMIR sign off engineer, methodology and flow engineer. So after completion of course of AMS means analog layout design, so you are become any one of this engineer like analog layout design engineer, standard cell layout design engineer, IO layout design engineer, and memory layout design engineer, RF layout design engineer. So core job opportunities in ASIC. So after completion of a course in ASIC or verification, so here you are become any one of this engineer, ASIC verification engineer or ASIC or FPGA or OTL design engineer, IP verification engineer, UVM verification engineer. Industry salary scope. So after training, you are become you get a chance in any one of the VLSA companies. So here as a fresher, you can get a package of starting of 4 to 6 lakhs. So if you have 3+ years of experience in the VLSA industry means you get an offers from product-based companies, that is NVIDIA, AMD, Qualcomm. So the minimum package starts from 15 to 20 lakhs. So if you have more than 5 years of experience in VLSA industry means you have become a team leader and the salary also very good, that is 25 to 30 lakhs per annum. And if you have more than 10 plus years of experience means you are become a team manager and the salary also very good, that is 60 to 80 lakhs per annum. Placement at Takshila VLSA. So we are having 200 plus hiring companies, including product, service, and startups. So MNC companies such as L&T, Capgemini, HCL, Wipro, Cyient, AMD, Synapsys, and many more service companies are there. So tool and interview support till you get placed. 4 to 6 lakhs of package minimum from our institute. So until you get a job, we will give you 100% placement assistance. So our placement process. So we get the requirement from the clients. So after that, we prepare the resumes of the students and send to the clients. So they will shortlisted according to their requirement. And the shortlisted students have to get ready for the written test, group discussions, technical interviews, and all. If once the student clear all the rounds means they are selected for the job. So until that, we will give the 100% placement assistance. So gateway for semiconductor industry at Takshila VLSA. So we are having 200 plus hiring companies that include product-based, service-based, and startup in that Broadcom, Mirror Technologies, Semi, Cadence, Capgemini, and Synapsys. So there are many more companies. So 2024 placed students from our institute, many students are placed in different VLSA companies. So here we can say these students have got industry highest salary as a freshers. So our students are placed in for all the domains like physical design, DFT, ASIC verification, almost all the companies which are there in Bangalore and Hyderabad. So 2024 placed students company was here. We can observe the Capgemini company hired 13% of students from our institute. Like that, many more companies like Digicom, Apex, Agastya Lab, Gapit, True Chip, Siliconos, Stencil. So almost all the students of our institute are there in Bangalore and Hyderabad in different VLSA companies. So contact us for fee and other details. So here that we are having two branches. One is there in Bangalore, other one is in Hyderabad. So corporate office in Bangalore, branch office in Hyderabad. So mobile number also given, email and website. If you need any information, you can note. So now we are entering into the technical part, which is related to VLSA, analog AMS or digital design flows. So types of IC. In VLSA, we are manufacturing two types of IC. So one is an analog and mixed signal. The other one is a digital. So in analog and mixed signal, it is a continuous signal. So it is varying as we are changing the input, output also changing. So for example, simple chips, audio processing, memories, and sensors and power. So sensors are good example, right? So they are continually varying. So that's why we are calling sensors as a analog and mixed. So comes to digital, complex chips, processor, wireless, USB, Bluetooth. So they are the discrete signals. So they are in the form of zeros and ones. So these two types of chips we are manufacturing in VLSA. So comes to analog IC design process steps. So here we are having two types. So one is a front end, the other one is a back end. And front end analog circuit comes under front end, and back end analog layout or custom layout. These two comes under the back end. So we'll discuss one by one. So analog IC design flow here. So here in these two types, one is a front end, the other one is a back end. So we'll see one by one. So in front end, analog circuit design comes under the front end. So here they will do the schematic. What is mean by schematic? Schematic is nothing but all the gates are in the form of and or inverter buffers are in the form of logic gates. So here we can see NAND gate. So these NAND gate are in the form of So here, like that, they will design the AND gate, NOT gate, inverter, buffer. So it is known as a schematic. So all the gates are transferred in the form of transistor. So that is known as a schematic. So once the schematic is properly right, means there is no errors in the design, means the work of the front end is done. So that is checked by the simulation engineer. So if they are getting any errors, means we are saying that the schematic design is wrong. So you have to do the again. So like that they will intimate. So it is the work of the front end. So again in backend, they will collect all this layout, means schematic, and they will do the layout. In layout is done by backend engineer. That is analog layout. So here they will designing of the nice shape, that may be any shape, rectangle or square, and they place all the cells which are there. So for chip making, we are having billions of cells, right? So all cells are they place inside the IC, and so that is known as a placement. And after that, we have to give the connections to each and every standard cells. So that is known as a routing. So place and route is known as a layout. It is a schematic that is transferred in the form of digital, means place and route. So after that, we will get some errors, means checks. So that are DRC and LVS. So these two are the checks. So why we have to check them, means while giving the routing, we are using the metals. So to do metals, we are having M1, M2 or M3. So the minimum, we have to maintain the minimum spacing, minimum width of a metal. If you are not maintaining that one, means we'll get the DRC issues. DRC means design rule check. So here we are using, we are checking the minimum space, minimum width of a metal. And LVS means layout versus schematic. So here, our design is two metal layers having like this. So it is an M1 and it is also M1. So when we are connecting, it is a one cell. Here also one cell. We have to connect them, these two cells. So here we are getting opens, right? So these opens are cleared by this LVS engineer or shorts. Opens or shorts. So these types of errors we will get while designing of an IC. So after that, parasitic extraction. So next, parasitic extraction and post layout netlist. So if we clear everything, means the work of the front end and back end is done. Otherwise, we have to, if we get any errors, means we have to check the place and route. We have to place in a different way. So still we are getting, means the schematic design is wrong. So we have to intimate that your design is wrong. So this is the work of the front end to back end team while designing of analog IC. So here we can observe the complete layout and schematic of an operational amplifier. It is a layout. It is a schematic. Digital IC or ASIC design flow. Until now we discussed about analog. Now we are discussing about digital. So ASIC application specific integrated circuit. It's a digitally circuit made up of a permanently connected gates and flip flops in a silicon, so that logic can't be changed. So why we have to connect them permanently? Means if we don't connect, if we not fixed any standard cells in the design, means so there is a chance of placing one standard cells in another place, right? So if we are placing, we are missing the logic and we will miss the performance of a chip. So that's why we have to connect them permanently. So nowadays ASIC has a complete system on it, often called system on chip. So why we are calling, means it is doing multiple tasks, right? One chip is doing multiple tasks. One is for process, video, audio, storing, right? So that's why we are calling one IC as a complete system on it. So here again we are having two types. One is a front end, other one is a back end. So in this, So here in front end, so RTL design comes under the front end. So they will take the specifications from the end customer. Like what type of specifications means uh, power, performance, and area. So our chip should be consumes less power and high performance and area also less. These are specifications. After that, RTL designing. So RTL engineer will write the code with the help of Verilog or VHDL, system Verilog. RTL designer will write the code with the help of combinational and sequential elements. And sequential. So combinationals are and or something and sequential are flip-flops or counters. So they will write the code like they will write the code of module. And suppose we are considering AND gate, right? So input A, input B, output. So equals to A dot B, N module. So like that, they will write this code, RTL code. After that, there is a verification engineer. So what is the work of the verification engineer means? They will give the different input vectors and they will observe the outputs. Whether we are giving the proper outputs for the given inputs or not, they will observe. So that is the work of the verification engineer. So after that, until the work of front-end engineer is done, so it will give the RTL code to the backend. That is to the backend means they will logical design engineer will collect the all the data. So here the backend engineer will do the synthesis. What is meant by synthesis is so converting RTL into gate level netlist. So RTL to gate level netlist. What is meant by gate level netlist? So they are in the form of logic gates. Like so these are the so like this they will develop. It is a gate level netlist. So RTL to gate level means code to this logic format. The synthesis team will convert. So that is the work of the logical engineer. Until now, the logical engineer will do. It is about the digital IC. After that, the physical design. So what is the work of physical design means? The physical design take all this gate level netlist. It consisting of the information of all the standard cells macros and that they will do the they will estimate the size of an IC that may be rectangle or square and they place all these cells in the block in one IC. So, and they will create the input output ports. So placing and giving the connections to each other with the help of metal is known as a place and route. You know that, right? So after this, physical layout means incremental placement. And that next physical verification. So we are using metal layers while connecting them, right? For that, we are getting electron migration issues. crosstalk issues, antenna issues. So the verification team will clear all these issues. So once the design is perfect without errors means the work of the front end and back end is done, and that is GDS2 format, GDS2 file is ready. Means graphical design system in 2D format. So it is ready for the fabrication of an IC. So these are the steps we are using while designing of an IC. So here we know that, right? So in that we are having two types. One is a front end, the other one is a back end. RTL, FPGA or ASIC design comes in a front end, ASIC verification, DFT. And back end physical design, physical verification comes under the back end. So specifications, you know that, right? Power performance area are the specifications which are given by the end customer. So chip specifications are driven by the end customer, so based on the requirement. So like some of the typical specifications are small size, high speed, low power consumption or any other new requirement to do the functions. So who will collect all the specifications means there is a one team like architectural team. They will collect the specifications from the end customer and they will develop the like block diagrams, flow charts or specific sheets. After that, RTL design engineer. So RTL means registers transfer level. So they will construct a digital design using the combinational and sequential circuit in a hardware description language. So such as Verilog or VHDL. So the above architecture is converted into Verilog or VHDL code. So our design is having many registers, right? So one register to another register, the data is transforming. So within that, we in one path we are having combinational cells. So for that combinational cells also we have to write the code. So this here we can observe the code of RTL code of a shifter. So RTL or ASIC verification. So here we are observing the by giving different inputs and observing the output, right? So that main work is done here. So architectural modeling, design specification, here the main work is done, and design under test, analysis coverage match with the expected results. So we are getting expected results means the work of the verification is done. Otherwise, again we have to give the different input vectors and we have to observe the output. ASIC test environment diagram. So how they will test means they will have the RTL code and they will have the test bench. So in our test code, they will have the RTL code here. It is an RTL code. And test bench, we are having clock. So why we are giving clock means our design is having sequential elements also. Without having clock means that sequential element can't trigger, right? So that's why we have to give the clock. And unit under test, BFM, bus for model, other models. So these are required while testing of the design. Design for testability. So here DFT. What is the DFT? What is the work of the DFT means? So while we are designing any objects or any things or means our design not getting 100% error free, right? We will get some errors in step-by-step process. That errors are identified this DFT engineer and they will add an extra code to the RTL design. So we'll see them once. So it consisting of a design technique that added testability features to a hardware production design. So DFT is a technique which facilitates a design to become a testable after production. So we will check them is a memory present in our design or not. So all these types of errors are checked by this DFT engineer. So it's an extra logic we are adding to the RTL code. So during the design process, which helps in the post-production testing. So post-production testing is necessary because the process of manufacturing is not 100% error-free. So there are some defects in the silicon, so which contributes towards the errors introduction in the physical device. So how they are uh, taking all these errors means with the help of scan chains. So what is meant by scan chain? So we are having two types of like we are connecting back-to-back connection of flip-flops. So there is some input scan enable and scan input. If scan enable is equal to 0, it will perform the functional mode. If scan enable is equals to 1 means it will perform the test mode. So these are the two types of mode which are used while testing of DFT. So physical design. Again, in physical design, we are having several steps. So one is a floor planning or partitioning. So what is meant by partitioning? Means our design is having many blocks. One chip having many blocks. That blocks are divided according to the hierarchical. So that is known as a partitioning and floor planning. So what is meant by floor planning? Floor planning is two types. One is a full chip. Full chip floor planning and block level floor planning. So if you have more than 10 plus years of experience in the block level means you can do the full chip. So here in floor planning only, they will estimate the size of an IC. Here, both. So here we are placing all the blocks. These are blocks. So here we are placing the macros. It is one block. Means any one of this block. It may be music, audio, DDR, or display. Because our chip is doing multifunctional, right? So for one function, we are having one block. So that one block we are taking here, that is a block level and that is a full chip. In here, we are placing all the macros. So for macros, we have to consider some guidelines. So the space should be, we have to take the minimum spacing, that is a channel length, because there is a chance of overlapping of the macros. So again, after placing all this, that comes under the floor plan. That comes under the floor plan. So in that, we have to create the input output ports. So through these ports only the power is entering into the chip. These are the ports. And here also we have to create the ports. So for block also power is important, right? So we have to create the ports. And after that, we have to do the power planning. So that is in such a way that the power should be goes in each and every block in the design. And here also the power should be goes each and every standard cells in the design. So it is about full chip, it is about the block level. So after the placement is nothing but placing all the standard cells in the design. So here billions of cells are there, right? All the cells are placed in the design. So that is known as a placement. And after that, we have to give the clock. Why? Because at the placement stage, all the cells, including combinational sequential cells, are placed in the design. So for that, we have to give the clock also. That is known as a clock tree synthesis and signal routing. So we are placed, until now we place each and everything. So for that, till now there is a virtual connections of each and everything. So we have to give real connection, means physical connections with the help of metal layers. So that is done in the routing stage, and later we will check some timings which are related like setup and hold. So these are the processes are there in the physical design. So physical design, what is meant by physical design means converting of a gate level netlist to the final production. So that is known as a physical design. Here the design cycle of VLSI consisting of different consecutive steps from higher level synthesis to lower. So here we are placing all the standard cells, right? So the physical design is a process of transforming a circuit with description in the physical layout, which describe the position of cells, and we are giving the routing with the help of metal layers, interconnection between them. The main objective of the physical design engineer is to generate a layout with minimum area. Means we are having PPA, right? Power, performance and area. So here only the power should be less and performance should be high and the area should be less. So these are the main three concerns of physical design engineering. Import design and initial checks. To do the physical design engineering, we have to give some inputs. So what are they? Means gate level netlist. Netlist. Constraints, logical and physical libraries, def file, scandep and UPF. So in gate level netlist, all the information of standard cells, how many standard cells are present in our design, and macros. So standard cells names that are reference names, instance names, and how many modules are there in our design or not, everything it is having. So what is meant by reference? For example, it is an AND gate, right? So the name is AND 2x2 inputs and HVT. So we are having high threshold voltage, low threshold voltage. So there are some flavors in for one cell. So that flavors are used according to our requirement. So these are the names. And constraints. It is having the clock information. So what is the period of clock and what is the input delay, what is the output delay, so what is the waveform of a clock, wavelength of a clock, each and every clock information present in the constraints, and logical and physical libraries. So here how much power it will consume for each cell, and area of a cell, where is the location of a cell, that may be standard cells or macros. All that information is present in the logical and physical library. So in def file, def means design exchange format. Here, so how many pins are there? What are the input pins? What are the output pins of a cells? All the physical information of a cells are present. And scan which is required, scan chain information is present in that. So which is required for the DFT engineer. UPF means unified power performance. Power format. So here our design is not working on the single voltage, right? So it is work on different voltage. So that's why we have to give them a UPF file for multiple voltage domains design. So these are the inputs we have to give while doing the physical design. Import design and initial checks. So here we are giving the inputs, right? So that netlist and Milkway libraries are dumped in this script. So there are some commands and scenarios. What is meant by scenarios? Mean power process voltage temperature. Our chip should be working in different temperatures, that may be cold or hot, and voltages. Our chip should be working in different voltage domains. So that related commands are dumped in this script. And after giving the start GUI, this window is opened. It is in ICC2. Shell. So here, these are the macros. So our design is having some macros. And these are the IO pins, input output ports. And all these purple color are the standard cells. So it is a layout window. All this area is a core area. Core area, I was spacing area is known as a die area. So here we know that floor planning is two type. One is a full chip and the other one is a block level. So here we are estimating the size of an each IC. So that having different blocks, right? So we have to create one block for another work like that, and we are creating the IO ports and we are giving the power. So that is in the full chip. Again, we have to do in block level also. We have to estimate the area for a block, and we have to decide the channel length for the macros, and we have to create the ports. We have to give the power planning. Floor planning, and here it is an internal structure of an IC. So these are the rings. One is a power ring, other one is a ground. So here, through these strings only, the power and ground like straps are there. So like this, they will go. So here, all the macros, standard cells, each and every are present. So to that, power is entering into the cells. So these are the straps. So here before slides, we observe that all the macros are at the 0, 0 position, right? So after doing the floor planning, they placed according to the all the guidelines of macro guidelines. And here see some of the settings like menu bar, toolbar, additive tool settings, and other settings. So here we can see port area, terminal, cells, pin shape, so everything. So as per our requirement, we can do any modifications. So here still standard cells are only at the outside only. Why? Because after placement only all the standard cells are placed inside the device. So placement is nothing man. Placing all the standard cells inside the core area. So the communication, they will see the location of the cells, and they will see the communication between macros to standard cells to macros, and IO port to the standard cells. So by observing all this only, they place at the one place. So they will see the power consumption also, each and everything. So giving the exact location in the core area to the all the standard cells in is called placement. So all the instances of the soft modules spread in the core area at this stage, placement is done based on the interconnected present of standard cells, macros, or standard cells to standard cells, and communication between IO ports. So timing and congestion issues are considered while doing the placement. So what is meant by congestion? So if you in a class there are only 10 chairs only, our students are 15 members. So there is no chance of placing them, right? So that leads to the congestion issues. So like that, we have to place without congestion issues in the a particular area, and all the cells need to be aligned to be placement grid. So here these are the goals of a placement. So after doing all the steps, we have to consider less utilization gem. Well, utilization means occupied area. So from 60 to 70% only considered while doing the placement, and no congestion issues, no overlap. So we should not place one cell on other. So it leads to the some issues, right? And no overlaps or legality, good timing values. So here there are some commands like place opt, which are related to placement, place opt, legalization, initial place. After giving these commands only, all the cells are placed inside the core area. So here we can observe them. So in before slides, all the cells are outside. After placement only, all the cells are placed inside the core area. So here they see the communication between standard cells to standard cells to macros, and IO ports. So after giving this script means the commands which are told in previous slides are dumped in this placement script. After sourcing that, all the cells are placed. So clock tree synthesis. So clock is given after the sequential elements. So here, why now we are giving means here all the sequential cells are present. For that, clock is required. So here we are creating the clock. So there is a create clock command. After giving this create clock command only, the clock is built. That clock should be goes each and every sequential elements in the design. So these are the sequential elements. So clock synthesis broadly classified into 3 types. What are they means? Clock tree, clock mesh, and clock spines. These 3. So we can give the clock in the mesh type also, or we can give the clock in tree type or tree structure also, and spine. So here source. So the clock is coming from the oscillator or PLL to the sync pin. So we have to give to the sync pins, right? So we are using some cells like clock inverter or clock buffer. With the help of these two cells, we can build the clock. Because a clock is a high switching element, so that's why we need some cells, that is a buffers or inverters. So clock to synthesis, while doing this, we have to consider some rules. What are they? Means define routing rule. So we are using the high metal layer for the clock to synthesis because it is a high switching elements. So the power consumption is more. If the width is more, means there is a chance of passing more electrons, right, in a metal area. So that's why for that we have to give the double space for the metal, because there is a chance of cross-talk issues, right? So that's why we have to give the double space and double width. Why? Because electron migration issues will come in future. So that's why you have to consider double space and double width. And define target insertion delays and target skew values. The target skew values nearer to the 0 but not 0. Because if the skew is 0, at a time all the cells, all the clock is triggered and there will be consume more power. If they will consume more power means chip will get heat and that leads to damage of an IC. Define clock cells. Here we are using clock inverters and buffers. Define routing rule. So here we are using high metal layers. If our design is having M1 to M9 means we have to use M7 and M8, M9 for the clock. So there is a commands, right? All the commands are dumped in the script. After sourcing this script only, we can build the clock. So routing. So until we see the virtual connections of a cells. But after routing, we have to give the physical connections, right? For each and every standard cells in the design. So for that, routing is done with the help of metal layers. So here, one cell is here, other one cell is here, and the next cell is here. So we have to give the connections like this. These are the metal. And there is another cell is here. So electric connections using the metals and wires are created in the layout defined by the logical connection present in the netlist. So here the different tasks that are performed in the routing stage as follow. So while doing the routing, we have to consider global routing. So global routing means it is a global routing. So we are not seeing all, we are directly connecting them like this. So in track assignment, they will assign the tracks. So in the particular track only, the signal should be goes. The metal wire should be goes. So that is known as a track assignment. And detailed routing. In detailed routing, it will suppose it is having the connections like this, right? So they will take the shortest distance of the routing to one cell to the other cell. And it may be leads to this like this also. So it will take this connection. And search and repairs. So in search and repairs, minimum space, minimum width, or shorts or opens will cleared. Means here they will do the incremental of a routing. So what is mean by via? So we are connecting them, right? So here, so these two are connecting. So they are intersecting, right? So this is known as a via. So routing. So after doing routing, there is a command. We have to check each and every process in the designing. So that is check ZRT routability. So after giving the check ZRT routability, we will get some errors. That is number of outboundary ports, number of main grid errors, number of blocked ports. If we have all these errors, means our design may get some errors, right? If we have all these errors in the design, so the performance should be will be less. So that's why we have to clear them. So that are cleared by the check ZRT routability, and we have to modify them. So all the commands which are related to route means route opt. route opt is a command. In that there is some more commands are there. All the commands are dumped in the script. So after that, the routing will be done. So physical design verifications. So here we have now until now we are discussing about the front end and the back end until physical design. Now we are entering into the physical verification. After designing, we have to verify them. We should not send that all the def into the fabrication. So we have to check them, right? So we will get some errors. So all that errors are verified. So in formality, we are checking the libraries, we are checking the net list, we are giving all these inputs, right? We have before giving the inputs, we have to check them, check. So that is known as a sanity checks. So check net list, check library, check timing. So all comes under the formality. And LVS. LVS means layout versus schematic, right? So in this, opens and shorts are checked by LVS engineer. And DRC, metals and vias, that is minimum space and width of a metal. Timing, that is setup and hold. Design rule violations. Here we are having capacitance, max cap, max trans. Errors are cleared by this DRV engineer and IR drop analysis. Here, while doing the routing, suppose here one cell is there and here one cell is there. If the metal wire is too lengthy means there is a resistance, high resistance. If you have high resistance means there is a voltage drop, right? If it is off means our design may not work properly. So that is cleared by IR drop analysis engineer. So these are the checks. Along with the checks, we have to check the antenna, electron migration, crosstalk issues. So these three issues also we have to clear in the verification. And some power. So my side, we are manufacturing two, right? So one is analog and one is a digital. So in these two, we are having both front end and back end. So front end is doing one type of work and back end is doing other type of work. So for that, we are using some shells, I mean tools. So ICC 1, 2, 3, ICC 1 or ICT 2, design compilers, prime time. For different work, we are using different IC. So and after designing of an IC, we have to check them. So after that, the GDS2 file is ready for the fabrication. If there is a zero errors means. So my side is done, students. If you have any queries means, you can ask. So what all will be covered in PD means, in physical design, you have to take the input means netlist, what I said, all the inputs, right? So while considering all the inputs, you have to design means you have to place each and every cells and we have to create the power ports and we have to do, you only have to do the power planning and we have to place the macros. After that, you have to give the clock for the sequential elements. So everything will be there. We are having the tools. So you know to get when you are taking the course only. Yeah, do we use any tools to check RTL like any test cases? Yeah, we are using the tools for for every design that may be front end and back end. We are having the tools like Cadence and Synapses tools. So test bench is provided by the industry. So do you have any more queries? So you can ask or you can drop a message in chat box also. So if you don't have any questions related technical or non-technical, I'm ending the webinar today. Thank you.
Hello everyone, very good evening. A heartfelt thanks to our speaker Sunita ma'am for sharing their valuable insights. I would also like to thank the HOD and students for their efforts in making this webinar a success. Looking forward more such interactions. Thank you all.